I'm going to get started. So I'm going to start with just a simple presentation, but while I'm doing that, everyone please make sure you have the tutorial materials. So the website is here on this paper. It's also here. If you've downloaded the repository before today, make sure you do a git pull so that you have the latest version, because we've pushed some stuff recently. And yeah, just make sure you have your environment set up so that you have SymPy installed. And there's a requirements file and an environment file. If you need any help, just raise your hand and help will come to you. All right, so yeah, welcome to the SymPy tutorial this year. So my name is Meurer. I'm a software engineer at Quansight, and I've been involved with the SymPy project since 2009. And I guess I'm going to plug my talk that I'm giving at the conference on Friday, which is not related to SymPy, but you should still come if you're interested in arrays. This is, maybe you want to just quickly introduce yourself, actually.
Okay. My name is Sangyub, and I'm a freelance software engineer at Bhat. And I'm front-end engineer, and I'm using Python and TypeScript. And I previously worked with other edutech like Tiger Make Education and Quanda team. Okay.
And how long have you been involved with SymPy?
Well, it has been like 3
remember?
years, but more than 3 years at least. Yes.
All right, so what is SymPy? SymPy is a Python library for symbolic mathematics, and we'll go into more detail what that means, but this is as opposed to numerical mathematics. So basically, exact mathematics like you would do on a chalkboard. So the difference between, say, computing the square root of 8 is equal to 2.8284 ... That would be a numerical library. It would give you an answer like that. SymPy will give you an exact answer, like square root of 8 equals 2 times square root of 2. And so SymPy covers a pretty large area of mathematics. We're going to have a list here in a bit of all the features. So here's an example. We'll see a lot of this, obviously, but just to give you an idea. So here's SymPy computing this integral sine of x squared from dx from negative infinity to infinity. So you see here SymPy can not only represent this integral, but it can actually compute it in a closed form as square root of 2 pi over 2. So the goal of SymPy is to sort of just be a general purpose computer algebra system, and while being also usable as a library and being easy to use from Python. So why would you want to use SymPy as opposed to maybe some other computer algebra systems that are out there, like Mathematica or Sage or any of these other systems? So, Sage is something we get asked about a lot, actually. So Sage is also open source. The difference with Sage is that Sage is actually an amalgamation of a bunch of different libraries, pretty much every open source math library, including SymPy. So Sage actually does include SymPy. SymPy itself is a standalone library, so it doesn't try to pull in a bunch of other things. But it is also full-featured. It's also BSD licensed, so that makes it usable for a lot of basically anything you want to do with it, whether whether you're using it for your own use or using it as a company. SymPy is probably the only system that really embraces Python as a language. So we're not, a lot of these other systems will try to build their own language on top of them, like Mathematica language or Maple language. SymPy is just Python, so there's no language that's built on top of it. And the last thing is that SymPy is also usable as a library, which we probably won't get into very much here, but we do have very strong support for use, programmatic use, and use as like a dependency of other libraries. So here's just a quick listing of some of the features of SymPy. I'll let you just glance through these, but sort of the basic things that you would expect a computer algebra system to do: polynomials, calculus, solving equations, combinatorics, discrete math, matrices, geometry, plotting, physics, statistics, printing. We're only going to get into a very small subset of this today, obviously, but the documentation will help you learn about what all is there. Why do people use SymPy? It's a great tool for education, both for teachers and for students. It's usable just as a sort of a calculator that does math a lot better than sort of just your typical pocket calculator. People use it in actual science to do to model their scientific problems and help them understand their problems. And we'll get into that a little bit with this code generation idea, where you can take a SymPy mathematical equation and convert it into code that can run that same equation and generate numerical outputs. And so SymPy ends up being used in virtually every scientific field, because any field that basically uses mathematics can potentially make use of SymPy. So right now we've had, I guess we don't have it on here, but SymPy was founded in 2005. Since then we've had about 1,200 contributors. There's about a dozen or so active people who are core contributors right now. There's about 690,000 lines of code and documentation in the code base, and over 500 pull requests merged last year. So it's a very actively developed project. We also have very recently gotten actual funding to work on SymPy, which we're excited about, from the Chan Zuckerberg initiative. We also have many Google Summer Code students working this year that I want to shout out to. Some of the projects that use SymPy Sage I already mentioned. PyDI is a dynamic modeling library in Python. PyTorch uses SymPy actually in the Torch Dynamo package, which uses JIT compiles PyTorch programs, and it uses SymPy to represent certain expressions as part of that. A few more. Octave Symbolic is the symbolic package for Octave. Geometric algebra, there's a Julia wrapper for SymPy. There's an open source Mathematica clone called Mathix. Yeah, I don't want to go over here, but here's a quick outline for today. We're going to have a few breaks, but to start up, we've got just the intro notebook. So all of our notebooks today are filled with exercises, so we want this to be an interactive tutorial. So please try to do the exercises. They're mostly not very difficult, so they're really made to just kind of get you typing and get you actually doing stuff so you remember. And all the solutions are in notebooks right alongside the actual instructional notebooks. So don't be afraid to look up the answers. It's really just about doing it, and seeing the answer is fine if you can't figure it out. Some of the exercises are like advanced exercises. Those are mostly just for those of you who finish early and want to sort of try your hand at something a little more difficult, but don't feel bad if you aren't able to get to those. But yeah, please raise your hand anytime you have a question. Feel free to interrupt us and ask. We want this to be interactive. So with that, we are going to switch computers and get started.
Can you show the outline?
Oh yeah, that's a good idea. And if anyone has had any difficulties installing stuff, please raise your hand. I'll come help you.
Okay. Can I just zoom in the notebook?
Make sure you're talking to the microphone.
Okay. How can I zoom in the notebook a little bit?
How can you do what?
Zoom in the text. It can be small.
Oh, Control Plus usually?
Yeah.
Control Shift, yeah.
But yeah, each browser zoom in. Okay. Okay. But it's okay. Yes.
I think you can hide this sidebar and make it a little.
Hmm.
Maybe you can move the microphone for him. So.
Okay. Yeah.
Just slide this, make sure you're talking into the microphone.
Okay, first of all, you need to check your installation. First of all, if you import the sheets and if you check the sheets version, you can make sure that it is something more than Python 3.9. I have 3.11 installed. Okay, but there is not much difference in this tutorial, but only for some Python syntax is different after 3.10 a lot. But it needs to make sure that you need to install the Python 3.9 such that you don't have any problem with importing the SymPy. Any questions? Okay. And the second thing you need to do is that you need to import the SymPy and check the SymPy version. And if you in this case, you must see the 1.12 version. You could have, let's say, more older version of the SymPy installed, but some materials of the tutorials can work, but I'm not sure that the results are exactly the same or something. Yes. So any questions about the installation? Okay. Okay. You want the presentation to zoom in more? Okay. Okay, and first of all, you try to begin with how to import the SymPy. Okay, SymPy pretty much can be used as some module than some other software to install, some library as Python. So you can just import the SymPy to use this. Okay, you can type in from SymPy import style, and it imports everything, every function inside the SymPy namespace. Okay, and for other math libraries or NumPy, you can also try importing, but this is not going to be used in the tutorial because much, but in this introduction section, it will be just imported to showcase what are the difference of the SymPy than other math libraries which are similar. Okay, and for example, if you type the math sign and sin pi divided by 4, it shows floating point result, and similar as the NumPy. Although the NumPy floating point can be a little bit different. Okay, in the data structure. But for SymPy function, for SymPy you get some latex result that represent the exact mathematics. And the reason that you can use the sign without any kind of SymPy prefix is that you imported SymPy with the style. Okay, this shouldn't be used in the practice, but in this interactive exercise, or you are only going to be using SymPy only, there is no ambiguity. So you can use this to make your program or your syntax more concise. You don't have to put every like SymPy or SP dot something in front of every math functions. Okay. Okay, but you can also do just do this by import SymPy if there is a lot of ambiguity of which function is from where. Okay, and we are just trying to introduce what are the common troubles you encounter in the Jupyter workflow. First of all, the problem is that if you assign the pi with something like 1, this changes the global variable and it changes the result. For this, or if you try to import the pi from somewhere else, we don't recommend to do this, but if you have done this, then you just try to prefix every code cells with from SymPy import style to overwrite them again. And then everything will work as clear as how the phrase SymPy imported. And if you have problems like if your notebook doesn't respond or if something like this happens, you would try to use the interrupt kernel. Okay. And also you can try to use restart kernel and clear output all sets. If you also want to clear the outputs of all set or everything. Okay, but I need to import this again because this really cleans up everything in the global namespace and yes. And to get help from SymPy, you would try functions like dir SymPy, which means, okay, this is SymPy imported. You can use dir for every Python objects or functions or modules and to see what the contents inside. And the reason you can do this is that SymPy pretty much have so many functions and so many things are inside. And this makes you unclear about if it is inside the SymPy or if it is inside some SymPy object or not. So you could try to check if dir to check what is inside the SymPy. Browse what is inside the SymPy. I think that there is something like auto-completion stuff to do this, but this can be explained later in the servers tutorial. Okay. This is too long though. And the other thing you could do is that if you want to browse the docstrings of the SymPy, you need to type help. Okay, and if you, for example, for the sign function, if you try help, then it shows pulls out the docstring and shows some examples on stuff that how you can use. Okay, I will stop recharging this mouse a little bit because it scrolls badly. Okay. Yeah.
If you click that blue thing on the left, the blue line on the left.
Okay.
Scroll bar.
Okay. Thank you. Okay. Anyway, and you can also get help from the IPython magic, the quotation mark. It is similar to help, but okay, it is for your preference. And the other thing you could do is that you can browse through the SymPy documentation website and try to search things like sign. Anyway, the SEO is the search is not very good though, but yeah, how can I find the sign? Okay, here. Okay, in here you can see more likely the structured documentation than the stuff like this, where it is written as some markdown plain text, but it shows things like latex formula and tries to put as some markup. So if you think that this is more better for visual, then you should browse the SymPy documentation. Okay. Any questions? Okay, let's move on. And we are going to be introduced on the symbolic computation. First of all, we are going to be introduced on the number system of the SymPy. The number system of the SymPy is different than the Python, and also with the other languages. Okay, in order to create a SymPy number, okay, the difference, the major difference is in the integers and the rational numbers. In order to create a SymPy integer, you can pass the Python integer to SymPy integer constructor, which is capitalized integer. Okay, and you can do the integer arithmetic as Python, similar as Python, but the result you are seeing is in the form of the latex. If you only do with Python integers, you just get the plain text. So this is the thing you can find the difference. You can distinguish. And SymPy integers have some other like methods like rich mathematical methods like checking whether this is prime or something. Yes.
So yes, you mentioned the word latex or LaTeX.
Yes.
And so line number 7. So is that like ASCII? Is that like some graphic text or?
LaTeX, but it is rendered by the Jupyter as.
It's rendered. Okay, so but the result from integer 12 plus integer 34 is that another integer or is that some weird string or what is the class or what is the type of? Yeah.
It is SymPy integer.
Oh, okay.
Okay. And the critical difference of the SymPy number system and Python is that about the division. From the SymPy, when you divide something integer to another integer, and if the division is exact, then you get just integer. And to divide, if the division is not exact, then you get the rational number. But in Python, you always get the floating point. And SymPy, for example, have something like prime factorization. Actually, the prime factorization is one of the things that is missing in the Python math library. So if you want to use the prime factorization in practice, you maybe have to install SymPy anyway. We have lots of things. Maybe we are one of the fastest library in the prime factorization. So yes, if you need prime factorization, you need to install SymPy. Okay, here are the exercises. These are pretty much simple, like create SymPy integers and find the prime factorization. Okay.
Line 16, what is 3:2?
Oh, it is the result of the prime factorization. We are putting in the dictionary where the keys are the bases and the values are the exponents. So this is like 3 power. How to comprehend the result is that this is like 3 power 2 times 101 times 301 times 3607 times 3807.
Power, okay, so that's
Yes.
comma is colon is power. When you multiply it, where commas are. Okay, interesting.
Okay.
So is that a list, or what is that?
This is kind of dictionary.
16 is a dictionary, the type?
Okay, this is a dictionary.
Python dictionary, not.
Yes, Python dictionary.
Okay, thank you.
Okay. Okay, and the second thing is that about explaining why do we need the rational numbers. The reason that we need the rational number is that in Python, when you do things like 0.1 plus 0.2, it doesn't equal 0.3, which is the reason behind this is that when you subtract this, you see very tiny error term. In SymPy, to avoid such like tiny numeric errors, and we are trying to do every mathematic exactly, such that every decimals try to sum to 0 or something. So that's why we are using the rational number as the standard for the SymPy number system. And if you are going to rather use the floating point, or if you are really going to use floating point, SymPy is not your best choice, and you would better use things like NumPy. Okay. And in order to create a SymPy rational number, you can just use the rational constructor, or you can just divide the SymPy integer like before. It is up to your preference. And you can add or subtract rational numbers, and it's try to, try to put the rational number in common denominator and tries to cancel out the things. Okay, here are the exercises about how to create a rational number and try to compute something simple. Yes. And the also other thing to notice that the rational number, like multiplied with something that gives exact integer, would give exact integer result.
So the operators, you can go up a little bit? So on line 24, we have operator plus, or in C++, we have the operator plus. So that's a special plus, obviously, because it's a SymPy plus.
Where?
Python lets you override operators. So, it's just a plus symbol.
Yes, the reason that this can, okay, the Python operator can be used to SymPy objects or even the things like NumPy or other libraries as such like arithmetic is because of operator overriding.
So is percent do modulo and stuff, or?
Yeah. Most of the Python operators are able to do that, which you'd expect.
Okay.
You don't actually have to use. Normally you don't actually have to use this integer constructor. Because it'll automatically sort of, if you add a normal Python integer to something that's already a SymPy type, it'll automatically convert it.
So it coerces it to SymPy.
Yes.
Any SymPy thing is
Exactly.
it'll coerce all the rest.
The only time you have to be careful about that is if you're dividing two Python integers, that'll create a float. So if you want a rational number, you should use like this rational constructor, or convert one of them into a SymPy integer first. Mm-hmm. Yeah, that will work. Yeah. Yeah.
Okay. Well, but it's a little bit.
Yeah, we should probably.
But the symbols are, yes, we need to explain the symbols, but.
I told you had too many material. You gotta go faster.
Okay. So the thing that about the integers and the rationals are not much, anyway, not much that special for the SymPy. The Python have things like the decimal library, the fraction library or something. They can also do the similar thing, but the what makes the SymPy special is about the symbols. The symbols are some kind of mathematical variable system that can be used to build some mathematical expressions or functions. Okay, in order to create a symbol, you can use the symbol constructor and pass with the string, which should be the name of the symbol. And you can check. Yes, this is like some LaTeX formula. Okay. And to create multiple symbols, you can use the symbols constructor. This is lowercase and it is plural, and try to pass the strings separated by the space. Okay. Anyway, you need to be careful that you need to always put the spacing between all the characters that you want to split. This is how we parse the strings and try to match up the how to break down the symbols. Okay. And the other thing useful is that if you want to create a Greek symbol, you need to use the the name of the Greek alphabet inside the symbol, and you can try alpha, beta, lambda. Yes, we have every Greek letters inside here. And the other useful thing is that if there are many symbols, you often use subscript. In order to create a subscript, you need to create a symbol with underbar. Okay, and after the underbar, you can put a number. Okay, here are the exercises how to create symbols. Okay. Any questions?
How does this, I mean, is this kind of, how do you all compare the work you all have done with the symbolic differentiation, stuff like that, with like what AutoDiff has been able to do, like in tensor flow models and stuff like that? I mean, I know you're doing it like fully symbolically, but I mean, how do they really compare?
So, yeah, so I mean, automatic differentiation is distinct from symbolic differentiation. So, like, SymPy tries to focus on being a mathematical tool primarily, so it's always going to try to do things that are sort of based on like how you learn them in like a calculus class or something.
Yeah.
And we'll see some of that later actually.
But it's still giving you an analytic result, automatic, but it's still just doing the computations numerically as opposed to symbolic.
Yeah, exactly.
Okay. Well, okay. That is not pretty much basic question though. Yes. Okay, here when you create the symbols, you can use this to build some SymPy expressions, which is the goal of this introduction section. Okay. First of all, the grammar to how to build a mathematical expression is that beginning with the symbols or integers or rationals. Sometimes this can be just Python integer, which are automatically called. And if you try to add symbol to symbol or symbol to integer or symbol to rational or integer to integer or something, then it gives expression. And similarly, subtraction and multiplication and division. This should be division though. And exponentiation, and also try to put into SymPy mathematical function with the SymPy expression that you have already built, then it also gives the expression. And many other SymPy functions that are too many to list here. Okay. And these are some examples of how to build SymPy expressions. First of all, you can build a polynomial. The way how this builds a polynomial is that x is symbol and x power integer is expression, and 2 times integer is expression, and this addition is 2 times x is expression, and expression plus expression is expression, and this is also calls to expression, so everything gets now expression and you get the formula.
Does order of evaluation play into normal math? I mean, like, is there a problem of order of evaluation, or am I overthinking?
It only depends on the Python operator precedence. Well, that is one of the let's say a tricky thing to do. Sometimes the reason why sometimes you have trouble dividing integer and integer, and sometimes you need explicit integer constructor or something is that the order of operation plays some role. But we can't override the order of operation in Python in some programmatically way, so we need to follow that. Yes. We can't really, let's say, change the order of operation. How
But you can use parentheses to change the order of operation.
well, that is already a Python feature,
Yeah.
and you can still put
You
up.
can do it in there too.
Yes. Okay, this is how it is done. And try to create the area of triangle. You need to use the rational. Or you can just divide by W times H by 2, and it gives the same result. Maybe this is more concise for you. But the caveat is that if you try to do this, then this gets a floating point. So this is why one of the things that you would need explicit rational constructor here. Okay. And in order to build a quadratic formula which involves the square root, you can pass the expressions you already built to square root and try to let's say obey the operator of precedence in Python. Yes, if you skip this parenthesis, you don't get the same result.
Shouldn't the quadratic formula be over 2a?
Okay. Yes, I actually forgot the quadratic formula when I written this a little bit. You can do this. Okay, the other thing that you need to be careful is that if you do this, this multiplication actually goes here. So it's the Python operator precedence that the multiplication division have the same precedence. So if you really do that, you need to do this trick. But if you don't want to, let's say, I prefer this style because it makes the formula more readable. Okay. And here are the exercises to construct the formula. And I just printed, let's say, some tricky things about putting the rational number on the exponential, so such that you need to sometimes create the integer to, let's say, mangle around the operator of precedence. Yes. Also, I noted an example about the division. Okay. Okay, we can skip other parts though. Yes, I would want to move to the next section, which the below is not very, let's say, important than the other things. Yes. Okay. And okay, if any questions about the exercise? Or okay, let's move on. Okay. Now, this is solutions notebook. Okay, now we are going to investigate the basic operation of the SymPy. Okay, in the prior section, you learned how to build the SymPy expression. Okay, we are reviewing this. But how to change the expression? You cannot do easily, like, you cannot do like, we declare the x with the symbol x, but even if we define x with symbol y, it doesn't change the original formula. And SymPy does not typically allow editing the formula because SymPy actually, all the SymPy objects are immutable. The only way to make a new formula is that you need to destroy everything and build something new. But this is not very programmatically way because you every time need to write a new code for a new formula. The programmatically way to do this is by substitution. We have built f here as x squared plus x plus here, one polynomial. And here, okay, you can use the source with the source symbol. And the first argument is source symbol, and the second argument is the target symbol. And if you do this, you can get a new formula programmatically. Okay. And because the SymPy expressions are immutable, the substitution or any SymPy methods does not change any original one. Although you can see that G is the new formula, you can still see F is intact. It's similar to how string replace work in Python. Yes, so you can say assume the SymPy behaves similar like a string. Yes. And let's say substitution can be more general, like the target can be some other SymPy expression, such that it gives some like evaluation result. And you can also try to use substitution with a dictionary to like let's say. Okay, this doesn't anyway have the Y symbol though. Anyway, yes. But the thing that you can do non-trivially is that maybe, yes, if this is multivariate, then you can substitute. No, this doesn't show the. This disappears. This makes everything 0. So yes. Substitute something selectively, like x substituted 1, it gives the only x value change it, and if y substituted 1, it only gets y value change it, and it gives the expression to let's say it gives, let's say, you can use this to multivariate substitution, like yes. And here are the exercises. Okay. Any questions?
So does this feel like all these strange calculus rules, like chain rule and this product rule? Calculus is one of the next sections. So the answer is it does know all these things that I was trying to memorize. Wow.
Well, yes. Well, substitution is more like algebra than, let's say, chain rule, which involves derivative, which is not learned right now. Yes. And yes, let's get to the next section, which is a numeric evaluation. Okay, in the Python math library, you only get like 70 digits of pi. This is a little bit hard coded. But how to get like 100 digits of pi or 1,000 digits? The way to do this in SymPy, you are possible to, let's say, not restrict pi to 70 digits, but 100 or 1,000 or whatever precision you want. The way how to do this is using the eval_f. And the first one, the argument of the eval_f can be blank still to give 17-digit result, but it can be arbitrary, let's say, integer which is the number of the decimal in this long evaluation. Okay, it happens pretty much fast. Okay. In order to evaluate the SymPy expressions numerically, you can do evaluation by the substitution, like in the sync function. And if you want to evaluate to the sync to 3.1 and get some decimal result, you can just use the subs you learned before, and it evaluates. Yes, but it doesn't also change the original expression though. But although I didn't put this on the variable, yes. Okay, the important thing to note is that unless as for the numeric evaluation, SymPy is trying to keep the formula as much symbolic as possible. For example, square roots and logarithms on exponentials and many math functions involves irrational numbers. And if you try to evaluate this to some numeric digits in some point, you lose precision, and you don't know like which number it originally came from. Like if I express a thing like golden ratio, if you evaluate to the eval app, although some people can guess this as golden ratio, but there can be lots of plausible guesses. So the reason that makes us to keep the expressions as symbolic as possible and not to evaluate numeric unless the user asks to do. Okay, the advantage is that if you keep everything symbolic, the mathematical identity is now about the numbers hold, like square root times power gets the original number. But in the math library, you don't satisfy this mathematical identity exactly because of the numeric errors. And similar, like you can also use this to represent the numbers like sine 1 or let's say invent many other arbitrary mathematical constants by just using the SymPy numbers by using the SymPy exact numbers. This is one of the examples, like you can just use the SymPy zeta function to define, to get the exact constant that you can define. Okay, math library doesn't have, let's say, every like math constant that are esoteric or something not common, only like pi or e, but in SymPy you can get every math constant. Okay, here are the exercises about how to expand the decimals. I just have the stuff, the rational numbers stuff though. Yes. Okay, any questions? And yes, I asked to expand to selectively to certain point of digits. Yes. The reason that SymPy allows you to selectively expand the numbers to the digit you desire is what makes SymPy non-trivial. Okay.
Is that a val f like a val formula? Is that one that comes both? Yeah, I think the name is borrowed from mathematics or something. I think it does stand for quote. When's the break?
Anyway, after this section, yes, we are going to be getting break. Anyway, we are just going to skip the parsing section because I don't think that it's very important for the rest of the tutorial, but we just go to the printing. Yes. Okay, mostly you get SymPy expressions evaluated to LaTeX in the Jupyter, but if you rather need a LaTeX code, then you need to use the SymPy printers. Okay. The SymPy printer that prints a SymPy expression to the LaTeX is this LaTeX operator. However, but this, if you just copy paste this to some LaTeX handler, this is not correct because of the escapes, like escaping the backslashes. In order to eliminate such things, you need to put print is just a Python native function, which evaluates this to row string. And you can copy paste this to get the exact formula. Okay. The other printers that SymPy have are pretty printing. This doesn't look good because there is no monospace font installed. Actually, you need some special monospace font, which is called Deja Vu Sans Mono, to be installed to be printed, getting this printed correctly. But anyway, but I would just use this Unicode, use Unicode force to just show as plain LaTeX, ASCII. And if you just want to print with the plain text, just use string. Okay. This looks, actually this is kind of, let's say, copy paste of a Python code that gives the SymPy expression exactly. Yes. Okay. And in the exercise, you are just asked to evaluate the SymPy divided by 60 and try to get this latex and try to copy paste in somewhere. Yes. Okay, this is all of this section.
Are we going to skip the last section?
Yes, we are just all because we are.
Well, here, I can show you what the pretty printing looks like because it doesn't work.
Wait, your laptop needs the.
Yeah, I know. We're just plugging it in.
No, you need.
Yeah, where's the cable?
Okay.
So yeah, the pretty printing, it's if you want to use the terminal, and it should show up soon. There we go. Let me make this way bigger. Yeah. So if you use SymPy in the terminal, then let's just sine of square root of x over 2. So yeah, by default it'll just use the string printing. There's this function you can use called init printing, which will enable the printing using this nice Unicode characters. So here's like a more, maybe if I take like the integral of this with respect to x, and yeah, so this is what that looks like. So yeah, it's actually pretty useful in the terminal, usable in the terminal, because we use these Unicode characters to pretty print things. But it's also really easy to use in the notebook because it just uses the LaTeX with MathJax. All right, so.
Can you make that, I'm not great at calculus, but.
Huh? Oh, I don't know. I don't know if this has a closed form. Yeah, I guess it does. So yeah, I mean, we'll see this later, but yeah, if I take the derivative of that, it should give back the original. I guess this is just a U substitution formula, so it's not that hard.
Well, I mean, integrate from one point to another.
Oh yeah. We'll go over that in the calculus section. I just wanted to show the printing. So yeah, I think we've got a quick break. Be back at 2:30, and yeah, if you have any questions or you want to.
Are you all like shipping as subset of LaTeX? Like how's that working?
The notebook includes a JavaScript library called MathJax that renders LaTeX in the browser. SymPy doesn't include LaTeX itself. It just knows how to print the expressions as LaTeX formulas. But yeah, the actual rendering that you're seeing in the notebook, that's part of the notebook. So that works even without SymPy. If you do like in a markdown cell, if you look at this exercise, if you just paste like LaTeX between $2 signs in a markdown cell, that'll render LaTeX. What SymPy is doing is this just kind of hooking into that for the actual output from the notebook. So that can be LaTeX as well. You have the next section, right? Simplification? Yeah, I'm just going to switch this back.
Okay, let's get started. Again. Okay. Okay, let's get to the simplification part. In here, we are going to introduce the SymPy simplification functions. Simplify in SymPy have various applications, like if you want to find some new mathematical formula, or verifying the answer, or changing the form of the mathematical expressions to get it more readable. Okay. First of all, to simplify, how I want to demonstrate the capability of SymPy, that how it can solve some complicated mathematical problem. First of all, you get this expression, which is not obvious to what kind of value it represents. But if you simplify this gets to 0. Okay, this is actually 0, but if you want to find how to see this is 0 by algebra, you need to denest the square roots a lot, and SymPy does this automatically. And the other thing about SymPy is that it can make some very complicated formula to be more readable. Like if I evaluate sin pi divided by 60, it gives very long formula. But if I try to simplify, this tries to, let's say, get it more compact. So maybe this is more readable than the above. So if you think that some formula are too complicated to read or to, let's say, copy paste on something, then you need to simplify. Okay. And simplify can be also used to verify some mathematical identities. Okay, I note the limitation of Python equality operator in SymPy. In SymPy, equality operator only compares the expressions are literally equal. What is literally equal is that x equals x is only true, or like sin x or equals sin x is only true. But the things like sine squared x and cosine squared x, okay, I need to execute this cell, is equals 1 needs some mathematical reasoning. But it is not done by SymPy. No, it is not done by the Python equals operator, because this only compares the expressions that are exactly equal, that are literally equal, like above. This is quite trivial. Or the below, where I can compare the polynomials where the left-hand side is expanded and right-hand side is vectored one. Okay. The way how to use the SymPy to test such expression to be equal is to subtract the things you want to compare and try to simplify. And if it gives 0, then it is equal mathematically. Okay, and this is one of the uses of SymPy. However, SymPy has some limitations. First of all, it can it doesn't simplify everything. That is one example is I can show below. Like if I try to use the numerator divided by denom, which is very complicated trigonometric expression, and even if I put to simplify, it doesn't give anything. But the answer is actually tangent 4x. But this is kind of issue of the SymPy or whatever. But you need to just see that the simplify, although SymPy gives a sound result, it doesn't always give a complete result. And the second thing is that SymPy is quite ambiguous. I mean, what is ambiguous is that which kind of formula is simple is quite subjective to people and context to context. Yes. And SymPy tries to find some arbitrary answer, but it may not be the best answer you are looking for. Okay. So in the following sections, we are going to discuss more specific ones about simplification function that you can commonly use. Even though in here you can use SymPy to do everything, here are more specific such that it does less ambiguous thing, and you can interpret the result more easily. Okay. First of all, we are going to introduce about the simplification method for polynomials. For the polynomials, we are going to introduce 2 polynomial simplification. One is expansion and one is factorization. The polynomial expansion is applying the distributivity law to the polynomial multiplication such that you can just see the addition of monomials. Okay, in here, we are going to, can just see, put this exp. Okay, we can just see this is original expression, but try to expand this polynomial, then you can get this 16-degree polynomial. Okay. Okay. The other operator that is useful for polynomial is about the factorization. Actually, expansion rules are quite mechanical, but vectorization are more involved. And like try to vectorize like things like higher degree polynomials or things are not easy. But in SymPy, you can use vector to vectorize any polynomials to put in the minimal multiplication form. Okay. You can try the vector with the exercise examples to see that it vectors things like 12 degree polynomials or very complicated multivariate polynomials. And you can see that it always works. Okay, any questions?
What's the time that we're supposed to?
Well, it's quite,
Oh, 25 minutes for this section, okay.
yes. Okay. And the next one that is useful as much as polynomial is the fractional expressions. What is the fractional expression? The fractional expression is the polynomial divided by another polynomial. Okay. There are like two useful operations for the fractional expressions. First of all is together. Together puts the addition of fraction to a common denominator. Okay. For example, if you want to add two fractional expression and put into a common denominator, then you can use together, and it tries to merge the denominator and puts everything on the numerator such that it is a single fraction. Okay, this is fairly a complicated expression, but if you can, okay, it anyway evaluates to 0 somehow, yes. But maybe this is really 0 with very involved calculation about the fractions, yes. Okay, and the below examples are much more complicated. But in here, I would also want to show that, okay, if you want to, let's say, expand the numerator and denominator also as a polynomial such that you don't see all the multiplication, unexpanded multiplication, then you need to use expand with the option break through. This is the original expression, and compare the result here, and you can see this is very concise result about this kind of this complicated addition. Okay. Okay, this doesn't have exercise though. Okay. Okay, below you are okay. There is another operator that is useful for fractions, which is cancellation. Cancellation is about for two polynomial expression on the numerator and denominator. It tries to find the common factors of it such that it simplifies the rational. Okay. For this expression where the numerator and denominator involves like the degree 4 polynomials, which is quite complicated. But if you cancel the numerator and denominator, then it simplifies the result. Okay. Here is the exercise for okay, the factoring, the canceling the rational number, which is fairly complicated, and there are two variables. Anyway, yes, to cancel such complicated rational expressions, you need to use SymPy to do this. Okay, any questions? Okay, let's move on. Okay, the next section is about some useful how to manipulate the trigonometry functions. 10 minutes. Okay. to manipulate the trigonometry expression, the algebra over the trigonometry functions are a little bit more involved than the polynomials. And however, but there is a useful function that is called the expand trig, which applies the, let's say, trigonometry addition formula and the multiple angle formula to expand the trigonometry functions as, let's say, cosine nx or something as only with the addition and multiplication of cosine x terms. This is one example. You can expand the cosine 3x into something. This can be arbitrarily large, like cosine 10x, and it can expand such complicated formula very quickly. Okay, here are the exercises. Okay, I also noted things like the addition of trigonometry expressions. Yes, if you try to apply expand trig for those functions, you can see that how this works and how the expand trig puts simplifies such expressions. Okay. Any questions? Okay. Okay, and the last thing about the trigonometry is about the trig simp. Trig simp is more involved than the trig expand. Trig expand is quite mechanical in any way, but trig simp is more like heuristic, and it applies much more trigonometry rules. Like you can expect everything in the Wikipedia to be applied somewhat heuristically, although it's not perfect though. Okay. The trig simp can be used to find identities like Pythagorean identities like sin x. Or yes, this is also introduced in the simplify, but the thing that it really does is in the trig simp. Yes, but even for more involved trigonometry functions can be also simplified like below, which is less obvious, but the SymPy's trig simp can do this sort of simplify. Okay, here are the exercises where the trig simp can be used to find some formula of more involved trigonometry expressions, and tries to, let's say, tries to apply many trigonometry identities to get this more, let's say, more mathematically more beautiful. Okay. We still have time, though. Yeah. The last thing is about assumptions. Anyway, this is a little bit important topic about how to use the SymPy because it. But we are talking in this section. The assumptions plays a role in the simplification. Okay, we are just introducing the polynomial or trigonometry, which actually the algebra rules about that actually works or for all complex numbers. But for the things like exponentials or logarithms or square roots, the algebra over such functions are not, let's say, does not apply globally to all the complex numbers. But you need some specific assumptions like whether A is like positive or A is real or something like this. Okay. Okay, to use the assumptions on the symbols, we are going to extend the how to create a symbol tutorial. In here, we are going to be passed with the arguments like real, true, or positive equals true, such that it defines the symbol in the set of reals or set of some positive numbers. Okay, without the assumptions, the symbols are just assumed to be complex, which is quite, let's say, which is quite general, but it is sometimes less specific. Okay. And the assumptions, with the assumptions, you can sometimes use the logical inference about what is positive or what is real or something. For example, if I use the real true and if I put x power 2 plus 1 is, if I try to query x power 2 plus 1 is positive, it tries to figure out this is true. And the symbol is positive. However, but if it is not sure about whether, like, okay, this x plus 1 in here is always positive because of the positive assumption and everything in addition. However, if it is subtraction, then it is conditionally true if x is bigger than 1. And this is not the exact same as x is positive. For these cases, it returns none, okay, which means that it cannot judge further. Okay. The way how the assumption system need to be, the way how you need to use the assumption system for SymPy is that if you want to simplify the functional expressions like logarithms, if you want to expand the logarithms and see the result, it doesn't try to expand the logarithm like x plus y, logarithm log x plus log y. The reason behind this is that this is not universally true for the complex numbers. Yes, you can just try to put, let's say, try to put x into something like some weird complex number and y into some weird complex numbers and check the values, and you can see what is wrong. Okay, so in order to simplify such expressions, you need to put the assumptions on the expressions. Okay, if I put a positive assumption on the logarithm, then you can see that it expands the logarithm. Okay, this is kind of more advanced simplified technique, but and we are not very involved in the functional simplification yet. But if you really want to do the functional simplification, then you can similarly use simplify, expand, or vector or something. But you also need to put some relevant assumptions that you want to that you could be missing. Okay. In the exercises, we are going to be introduced about you are going to do how to define some symbols with assumptions and try to expand the logarithm x powers n to n log x, which anyway needs to involve assumptions. Okay. And yes, I haven't explicitly said that which one is the correct assumption to vector this out correctly, but you can figure it out. And try to figure out, let's say, more general one then. Try to put everything like x or n into positive or something, yes. Okay, that's all about the simplification.
Switch over while you do the questions and exercise.
So my math isn't great, but I know that sometimes you have this thing plus or minus in front, and it's got to do with absolute values and square roots. You know what plus and minus? Have you put that in front of something? It could be either positive or negative.
Yes.
Does this system understand that, or you have to avoid it by saying assume positive or something like that?
Well, the system tries to figure out, let's say, in the example I showcased, if x is real, it can figure out like x squared is positive, and this added to some other positive expression is positive. It has some kind of heuristics to infer such logics, but it is not very perfect or not that much powerful like some things like SMT solver. Like SMT solver, like some theorem provers that can prove everything. But in SymPy, it only proves like, it only have capability of proving quite partially.
Oh, I see. So there's other provers that I've never heard of. Okay.
All right. Any questions before we move on to the next section? Otherwise, let's move on to calculus. So from here on out, we're just going to sort of define X, Y, and Z as our symbols that we'll be working with throughout the notebook. So the main things we're going to cover here are differentiation, symbolic integration, limits, and series expansion. So first off is differentiation. And so for that, we have the diff function. So diff takes an expression and the variable you want to take the derivative with respect to. You can also use diff as a method, in which case you just pass the variable as the argument to the method. So these are the same thing. SymPy automatically will treat any variable as a constant unless you tell it that you want to take the derivative with respect to it. So there's no notion of like constants or variables. It's all just depends on what variable you pass to the diff function as to what's considered a constant or what's considered a variable. So for example here, if I take this sine x times cosine y, I can differentiate that with respect to x, or I can differentiate it with respect to y. To take multiple derivatives, you just pass the variable multiple times. So for example, to take a third derivative, you would pass x 3 times. You can also put the number here after the variable if you don't want to type it 3 times. So here's a function, second derivative, you just do xx, or third derivative, you can do xxx or x comma 3. You can also take multivariate derivatives, so I can take the derivative with respect to x and then with respect to y, the partial derivative here of this expression. So, SymPy also supports representing derivatives, unevaluated derivatives. So if you don't actually want to compute the derivative, but you want to just represent it, you can use the derivative class with uppercase D here, and that will not evaluate automatically. And so if you have something like that and you want to evaluate it, you can call the .doit method on that, and that will cause all the unevaluated things in the expression to evaluate. And so you also, if so I guess so you can also, if it can't compute the derivative, which for derivatives, pretty much the only case it's not going to be able to compute it is if it's an unknown function. It'll just return unevaluated. So in SymPy, you can, to create an unknown function, you use this function class, and so that will create just a function that is just an unknown function. So you can do f of x. And so if you want to represent like an ordinary differential equation, instead of using like y as your dependent variable, that's not going to work, because if you do try to take the derivative of y with respect to x, SymPy is just going to treat that y as a constant. So instead, you need to use these undefined functions and explicitly say that your function depends on x by using f of x. And then that will create this thing. And this is this object here that is this derivative object that was mentioned above. And so sort of the general rule that we're going to see in this notebook in particular is that the lowercase version of the function will evaluate. So for example, diff. The capitalized version does not evaluate. So this, for example, the derivative object does not evaluate. But you can force the unevaluated version to evaluate with the do-it method. And whenever the lowercase function can't compute something, instead of giving an error, it will just return the unevaluated form. So if you see an unevaluated form, that usually means that SymPy just wasn't able to compute it. And you can always verify that by calling do-it to try to force it to evaluate. So here's some exercises. Compute the following derivatives of these functions. I probably should have made these all the same. So yeah, so there's no different function for partial derivative. It's still diff. To do a partial derivative, if you do a derivative, if you just do different variables that you're taking the derivative with respect to, it'll treat that as a partial. But the diff function does both ordinary derivatives and partial derivatives. They're both basically computed in the same way, so they're not separated. They will print differently though. So for example, here, if I have just an ordinary derivative, it uses this d, and if I had like a partial derivative, it would print with the partial. But yeah, the distinction is something that doesn't really matter for what SymPy is doing in terms of symbolic evaluation. So they both just use diff and derivative. Okay. Yeah, maybe I'll just open the solutions to show them real quick, unless people are still working on them. But yeah, and I think I was intending to make all of these the same function, so I don't know why I didn't put that y there. Oops. But yeah, so the solution here is. Oh, I guess the reason is to show that this is a regular derivative and this is a partial derivative. But again, they're the same thing. SymPy doesn't really make a distinction between this y being a variable that's different from x and being a constant. They're both basically the same thing. So these are both the exact same. Just take diff this expression comma x. There's a advanced exercise here, which you may feel free to do if you finish early, I guess, on the other exercises. But I'm going to skip over it for now because yeah, it's a little more complicated. And let's go to symbolic integration. So integration, the opposite of differentiation, but in terms of the syntax, it works very similar. So there's an integrate function, and you pass the expression you want to take the symbolic antiderivative of, and then the variable. And note that integrate is not going to it's not going to show the constant of integration, but obviously it's still there mathematically. So it's just going to give you technically it's going to give you a integral, not like the integral. But that's something to be aware of when you're using it, that sometimes it might give you something that's a little different than what you expect. So for example, a textbook might say that the integral of sine x cosine x is like negative cosine x squared over 2, but integrate will tell you it's sine x squared over 2, which seem like different expressions, but they actually only differ by a constant. And you can verify that actually by, say, using simplify. So if I simplify, say, sine x squared over 2 minus negative cosine x squared over 2, they differ by a constant. So this would be like this plus, if it, really this should be plus, this should be like plus c, would be sort of the more mathematically correct, but SymPy doesn't include that for you. So you just need to remember that it's there. The other kind of integral that you probably want to do is a definite integral, so something with limits. And this uses the same function. The only difference is now instead of passing a variable, you're going to pass a tuple where you have the variable, the lower limit, and the upper limit. So here I'm taking the integral of e to the negative x dx from 0 to infinity. I guess we didn't cover it yet, but infinity in SymPy is represented by just OO, which if you look at it closely, you can see why that is. It's a lot easier to type than infinity. So, yeah, just to sort of prove that this is OO isn't. Yes. Uh-huh. Well, so that it would be easy to add the constant. It would be less easy to remove it if you don't want it. So SymPy opts to let you include it if you really want it. But if you say have an integral that's part of a bigger expression and the constant's already included in that somehow, then it's not going to be there. Now I don't think we cover it here, but SymPy does have functionality to solve ordinary differential equations. Maybe maybe I can just show you real quick. So there's this, I don't know if I have F defined. Yeah, I do. So if I have like a differential equation, like say, derivative of f of x equals x, equals f of x. There's a function which I called dsolve, which will solve this differential equation. And dsolve actually does include constants. But yeah, integrate is sort of treated more as like a lower level function that doesn't do this. And this will internally, dsolve will call integrate and then add the constants. But for example, suppose you had two integrals added to each other, you would end up with two constants added to each other, but really that should just be one constant. You would have to simplify that. So it's typically when you have like a larger formula with some definite integral, or indefinite integral, that's already going to include the constants in some way because it's going to be coming from, say, like an ODE or something. Mm-hmm. This is C sub 1. It's not. Oh yeah. So well. Yeah. So I mean, you could do like this if you really want. If you really want to say integrate e to the negative x, or what was the function I had up here? I guess it was just sine x. If you really want to, you could represent this integral as as this ODE, and then solve that ODE with dsolve, and that will give you something that includes a constant. But yeah, so like with derivatives, you can do unevaluated integrals with uppercase I integrate, or capitalized I guess. And just as with derivatives, if you want to evaluate an unevaluated expression, you use this do it method. This is just to show that SymPy can do some advanced integrals that you probably wouldn't know how to do by hand. So integral of sine x squared, you would probably need to just like print this to even see what these functions are. So this is the Fresnel S function and the gamma function, and you can look in the documentation to see what those are. But unlike with derivatives, there's if you just do some random expression, it may not have an integral, or maybe SymPy doesn't have the algorithms to compute it because a lot of integrals require fairly complicated algorithms that SymPy doesn't have implemented yet. So if in that case, you'll just get an unevaluated integral back. And so you can see if you print this here, you can see this is an unevaluated integral. So when integrate returns just an integral object, that means that it wasn't able to compute it, which could mean that it doesn't have a closed form, or it could mean that SymPy just doesn't have the algorithms to compute it. And so now your exercise is to write a function that produces a nice integral table. Yeah, you can use, to display the answer, you can use like the pprint function, or you can also use this display function. Is it lowercase display? Yeah, so there's this function. This is part of IPython, or the notebook, not part of SymPy. This display function you can use it inside of a function, and it'll display it in the notebook with LaTeX, or however it gets represented in the notebook. What time did I say for, oops. How do I get out full screen? Okay. Oh, and this text is not supposed to be in here. So ignore that and sell. That's a leftover from a previous iteration of this. And there's also an advanced exercise here if you finish early and want to try that out. This one's not too difficult compared to the other one. So I'll just show the solution for the, oh, I don't have the solution for that one. Never mind. Oh, here it is. It's underneath. Yeah, so here we just manually create a constant of integration and then display. I guess we haven't gone over yet. The EQ function does equality. We'll go over that more in the solver's notebook. And we use on the left-hand side an unevaluated integral, and on the right-hand side an evaluated integrate. And then, yeah, I'll leave this other exercise if you're interested. All right, we may not get to series expansion, but that's okay. Any questions? All right, well, so the next calculus thing is limits. And so the limit function computes the limit of, it works like limit function variable point. So to compute the limit say, sine x over x, as x goes to 0, you would do sine x over x, comma 0. And then a quirk about SymPy is that by default, limit computes only a limit from the right, which is this plus sign. So if you actually want to compute a bidirectional limit, you have to do this direction equals plus minus, which if the limits are equal, if the limit exists, that will also be the same as the limit from the right. But if, for example, if the limit from the right and the limit from the left are different, you'll get only a limit from the right by default. So say limit of 1 over x as x goes to 0. By default, if I omit this, by default it's just going to give infinity. And then, yeah, if I change this to a bidirectional limit, I'll get this complex infinity object, which it represents the North Pole of the Riemann sphere. Oh, sorry. Yes. So that's a squiggle. So if you haven't studied complex numbers, this may be a new mathematical concept, but basically, yeah, in the complex plane, there's sort of just one infinity, which is the infinity sort of in any direction. You can imagine sort of taking the complex plane and wrapping it up into a ball, and then the very top of that ball is the complex infinity. And so since SymPy works with complex numbers by default, it has this complex infinity to represent that. And yeah, if you want to make that object, this is ZOO is the name of that. Yeah, I think that's right. So, well, normally if I just do 1 divided by 0 in Python, you get a 0 error. But if I do integer 1 divided by integer 0, that's actually going to give complex infinity. So that just makes things work out a little nicer in SymPy. And so the main reason to care about limit is that sometimes when you want to evaluate something and there's a singularity where you're evaluating, if you just use subs, as we showed earlier, you might run into problems. So for example, this function x squared over e to the x, say we want to evaluate that at infinity, you can see that that's going to give you infinity over infinity. And so if we just plug that in with subs, it's just going to evaluate it sort of naively, and it'll get infinity over infinity. And oh, I didn't do this. So, yeah, SymPy, that's just going to give this nan object in SymPy. If you ever see this nan object in SymPy, it means that you probably evaluated something somewhere where there's like a singularity and you need to use like a limit or something to be more precise about it. So if instead we use the limit function to take the limit as x approaches infinity, we'll get sort of the answer we expect. And this can happen at this doesn't necessarily just happen to happen at infinity. For other kinds of expressions, it could happen at any number. So just, yeah, something to be aware of. I think this is one of the advanced exercises, so if you if you want to give it a shot, go for it. But otherwise, I think we're at the break time, 3:20, right? So I just yeah. So yeah. So. Unless there's any questions, we can take another quick break. Yeah, and I think if you want to learn about series expansion, you can read what I have here, but I don't think we have time to go over it. And what's after that? Oh, so solvers. Okay. So yeah, at 3:30 we'll start again. All right, well, I think we'll get started again. So the next notebook is about solving equations. And so, yeah, so to represent an equation in SymPy, I think I showed this already, but you use the EQ object to represent a symbolic equation. And this is important because the double equal sign does not represent a symbolic equation. This only, the double equal sign is used to test if two things are exactly equal or not. So double equals is always just going to return true or false. It's not going to actually give you an equation. So to solve an equation, so by solve in SymPy, we mean to solve an equation to sort of isolate a variable in an equation. To do that, use the solve function to solve an algebraic equation. So you just pass the equation and then the variable. And solve will return a list. And so actually something I should probably note is you may have noticed up here at the top, I call this function init printing. So if I don't call this function and I say do that, restart the kernel. So by default, any SymPy expression in the notebook will render this nice LaTeX form. But if the type of the output is not a SymPy expression, it won't do that. So solve returns a list, and because a list is not a SymPy type, it's just a Python type, it's not going to render as LaTeX just because this is the way the notebook works. So the notebook just looks at the type of whatever output and checks to see how that type is basically registered itself to print in the notebook. And Python lists don't know anything about being SymPy. And so what this init printing function does is it just hooks, hooks into the notebook so that built-in types like lists and integers and booleans will also print with LaTeX. And so that's why when I call that function now, we get sort of the LaTeX representation of the list. So normally you don't really need to use this because SymPy objects will always just print as LaTeX, but if you want things like lists and stuff to also print as LaTeX, you need to call this init printing function. And so since it's a list of solutions, if you want to access each individual solution, you just index it like you would a list, or you could iterate over it. It's just a normal Python list, so you use it the same way you would any Python list. And so if we want to check that these solutions are correct, we could plug them back into our equation using subs. So substitute x with, say, this first solution. And since this is an equation object, when we substitute it in, ideally we should get the left side is the same thing as the right side. And so that's why this is just evaluating to true, because it's an equation object. So yeah, so these equation objects are kind of nice. That's how we usually think of solving things, but it's also they're kind of annoying to work with because you can't like add two equations to each other, or add something. If you want to manipulate an equation, you need to basically use like these LHS and RHS attributes to access. Oh, what happened? Where'd it go? Here we go. The LHS and RHS attributes to access the different sides of the equation. So actually what you typically want to do when you're using solve is, instead of using an equation, you can just use an expression that's equal to 0. So basically subtract one side of the equation from the other. So instead of x squared equals y, I'm just going to use x squared minus y. And because this is an expression, solve will just sort of automatically assume that it's equal to 0 and solve that. And so that's going to give us the same thing. And so, for example, if we take this x squared minus y, So let's say this is our second solution. If we take this x squared minus y and substitute the equation, our solution into that, we should get 0 if it's correct. And I don't know what happened to the exercise here. Okay, well, if you want to see the exercise, you have to open the solution notebook because they somehow got deleted. Yeah, the exercise is to solve these equations for x. And actually to solve this last equation 2 times, once for x and once for y. Nope, I keep hitting this. Okay, well, just to quickly go over the solutions, just remember that you can use just this first thing equals 0, so you can just put it in directly. You don't need to use equals 0. And then for this tangent of x equals sine x, I can either use an EQ object, or I can just do tangent of x minus sine of x. Yeah, I think this solve set thing is something that I haven't mentioned yet. So there's a few important things that you need to be aware of when you're using solve. The first thing is to just remember that SymPy is focused on symbolic exact mathematics. So solve is only going to give solutions that are the exact mathematical solution in a symbolic form. And so it'll do this even if the solution is some crazy expression that's way more complicated than what you were probably looking for. So for example, to solve this polynomial x to the 4 plus 4x squared minus 2x plus 1, the solution to that involves the general quartic equation. And so this is what the solution looks like. There's 4 of them. And so if all you care about is a number, then solve is actually kind of overkill here, because really you don't actually need all this complicated expression. And so you could evaluate this using eval-f, but the bigger problem here is that sometimes solve just can't find a solution, and that's sometimes because there's no algorithms, and sometimes just because there isn't a closed form expression for the solution. So for example, cosine x equals x doesn't have a closed form solution. And we can, if we use the plot function in SymPy, we can verify that it does indeed have a solution. You can see it goes through 0, but there's no closed form answer for it. And so if all we wanted was the numerical answer for this, SymPy solve is a bad thing, a bad tool to reach for that. And we'll go over in a bit what a better option would be. But if you're explicitly looking for symbolically solving an equation, that's when you want to use solve. Yeah, so I've plotted cosine of x minus x. I mean, I guess I could also plot cosine of x and x, and you can see that they intersect. So another issue with solve is that solve might not return every possible solution. So for example, sine of x equals 1, which is here sine x minus 1, has infinitely many solutions, but solve is only going to return one of these. And so there's another function in SymPy called solve set, which works similar to solve, except instead of returning Python objects, it will return the symbolic set objects. So this here is a set representing the full solution set to this equation. So 2n pi plus pi over 2, where n is every integer. So usually you actually want to use solve just because the output of solve is a list and it's a little easier to work with compared to the symbolic sets. But if you want to be sort of more mathematically precise, you can use the solve set function. Oh, and this is what happened to the exercise. Okay. So actually, yeah, if we go back to the exercise, we can see that when we solved tan x equals sine x with solve, we only got some of the solutions. But if you use solve set, you'll get the infinite solution set, which is the symbolic set object. So yeah, if you only care about numerical answer, just like a floating point number, you're better off just using a numerical solver. And so you can use a solver from a library like SciPy, and we'll go over how to do that, how you can still use SymPy and do that in the code generation section later. But SymPy also has this function nsolve, which can do it directly. So nsolve takes an expression, and then the second argument here, unlike with solve, it's not the variable you're solving for. This is a starting point that is a guess, is something that's close to the solution. So if you're familiar with something like Newton's algorithm, this is going to be sort of like the initial point that it's going to use. And so this is the solution to this point. And so, yeah, here's an exercise to solve these equations with nsolve. Yes? So there's a library called MP-Math, which SymPy uses to do its numeric stuff. So MP-Math stands for multi-precision math. So it's MP-Math is a library for doing arbitrary precision. So that's how SymPy is able to do like pi to 1,000 digits, is because this MP-Math library implements the algorithms to compute numerics to any precision. And so, yeah, SymPy doesn't actually use NumPy or SciPy by default. There are ways to interface with it, which we'll go over later, but by default, it doesn't depend on NumPy or use NumPy internally, because NumPy only uses like a machine floating point, like a float 64. And the problem with a float 64 compared to like an arbitrary precision float is that when you lose accuracy from a machine float, there's no way to like get more precision to get a more accurate answer. Whereas internally, SymPy can use MP-Math to compute things numerically to any number of digits that it needs to get an accurate result. Yeah, so nsolve is going to be able to, I think there might be a precision keyword argument. Not actually sure for nsolve. So nsolve is actually just a wrapper around an MP-Math function called, it should be here somewhere. Oh yeah, I guess if you want to increase the precision in nsolve, you have to sort of do it manually. npmath.findRoot. Yeah, that's something I think that we could probably improve to make that a little easier. But SymPy, like the focus on SymPy is always on symbolic stuff. So these numeric things like nsolver, they're more sort of just like helper functions or like convenience things if you really want a numeric answer. But like the focus is really on getting symbolic answers. And if you're looking for floating point answers, you should either use NumPy or SciPy, or if you want the higher precision, you could use MP Math. So here's the.
How high precision do you have?
So by default, SymPy uses like 15 digits. It's the same precision you'd get from a float 64. But you can do any precision you want with this. Like with eval_f, you just pass the number of digits you want, and that'll give you a higher.
Like 128 or something like standardized?
So that, yeah, MP Math has its own representation of floating point numbers that doesn't use actual like machine floats. It uses integers to represent an arbitrary precision. If you look at the MP Math documentation, you can read about how it's implemented there. Okay, well, so yeah, Solve also supports solving systems of equations. So to solve a system of equations, you pass a list of equations and a list of the variables. And then I also recommend passing this flag dict equals true. And what this dict equals true flag is going to do is it's going to force the output to be a list of dictionaries. If you don't pass this, the output will differ depending on what the solution set looks like, which this sort of forces the output to always be the same regardless of what the actual output is. So it sort of makes it easier to work with programmatically. It's always going to be a list of dictionaries, even if there's only one solution. And so, yeah, just as with Solve, if you want to access these, it's just a list, and then the dictionary keys are the variables. So, for example, I can iterate through this list, and then each solution is a dictionary. So I can access, say, like the solution, the X solution is solution this with the X key, and the Y solution is solution with the Y key. And so the nice thing about this dictionary representation is that you can just pass it directly to subs to substitute it. So say if we wanted to substitute this back into the equation to check that it's true, we can just pass the solution directly into subs, or we could substitute it into another expression, for example. And so an important caveat with solving systems of equations is that most systems of equations don't really have closed form symbolic solutions unless they're linear systems or polynomial systems. Or even if they do have one, SymPy mostly only has algorithms for those two. So if you just have some system of equations, but the variables aren't linear in those equations or polynomial in those equations, Solve is typically just going to fail. So for example, if I take this system of equations, I have no idea if this system has a closed form solution or not, but Solve gives us not implemented error. And whenever you see not implemented error in SymPy, it means that it's just, there's nothing implemented to do. It means you have to try something else. Or it could also mean that it just doesn't have an answer. Or it could mean that there's an answer, but it's not implemented yet. But yeah, you can also use nsolve to solve a system of equations. So you pass the list of variables and the list of starting points. And so there's an exercise to solve this system with Solve. And yeah, I think we're actually a little ahead of time, so that's good. So yeah, if you have any questions, otherwise let's move. I think the next section is you, right? Yeah. Well, and then I'll pull this back up so you can see. if you finish early, we can break early. Otherwise, just go to 4:20.
Okay. Okay, in this section we are going to
Move the microphones.
okay. Okay, in this section we are going to be introduced on the matrices. Okay. In order to create the matrices in SymPy, you need to use the matrix constructor, and you need to you can pass the list of lists that resembles the matrix structure in the Python object. Okay. Or if you just only want to construct a single vector, then you can just pass a list. However, but the thing is that this is actually a matrix of 3 rows and 1 column that is represented internally, even though the vector is not nested. Okay, and it is the same as, let's say, try to put the square brackets all over the place to okay, same, but this is, let's say, more verbose, so you can just prefer writing like this if you see how this is working. Okay. And another way to construct a matrix is that you can construct a matrix, let's say, with functionally. Okay. And you can specify matrix with different arguments. First one is the number of the rows, and the second one is the number of the columns. And the third one is the function that takes the index of the row and the index of the column and gives the result. Okay. However, but the ij begins with 0, 1, 2, 3, and 0, 1, 2, rather than it starts from 1. So you need to be careful about this. Okay. And the SymPy also have some special matrix constructor, like if you just want to construct the identity matrix, it can also be done like okay, this should be square, so yes, the I really does things like this behind, but if you just want to construct identity matrix more concisely, and the I is the thing that the NumPy or the NumPy is using, so you can create a similar like this. And also we have ones or zeros to construct the 1 matrix and the 0 matrix. And diag, it constructs a matrix with the specified list of arguments in the diagonal entries. It always constructs a square one, but ones or zeros, it have option not to construct square ones. Okay. Here.
So actually, you can do black if you have to press. So that's kind of an advanced.
Well, yes, but it's more obvious to, more simple to be, yes, mentioning. Okay. So here are the exercises about how to construct the matrices. You can prefer putting the, using, just writing down every entries of the list, or using things like functions. But yes, but it's all for your preference, but sometimes it can get really large. Or, yes, like if you just want to create an identity matrix over 10 size, then you would just prefer using the functions. But if you want to create the matrix like this, where the entries are not obviously functional, then you would not think of how to create a function that does this, then listing the entries explicitly. So yes, it's up to your preference. Okay. Any questions? Okay. And we have a few basic matrix methods. A few basic matrix methods are about indexing the matrices and adding and multiplying. Similar as the NumPy arrays, SymPy matrices are two-dimensional arrays. So to index to get the matrix entries, to get the entry of the matrix, you need to pass the index of the row at the first argument of the.
You showed the definition for A there.
Okay, A.
Just do a column, just do a cell and type A so we can see what it says.
Okay. Anyway, okay. This A is already defined as a matrix somewhere, though.
Yeah, that's why I don't want you to show it again because it's not, you can't see it.
Where I wanted to copy paste this one.
Just add a cell above that one and type A in the cell.
Okay. Okay, this is the A, and if I can access the entries of the A as this index. Although the A looks like A is defined as some vector, you always need some second argument as 0 to be, because this is actually a matrix with only one column. Okay, but the thing is that you cannot use the NumPy index like ij separated. Where that is because SymPy only, let's say, have a two-dimensional arrays, and we don't have like the actual representation of one-dimensional arrays. And you always need to access the matrix as thinking that everything is two-dimensional or scalar. Okay. And in order to get the rows and columns of the matrix, you can use the a.rows or a.cores or a.shape. Okay, this is useful for if you want to write some for loops and want to find some bounds for the iteration. Okay. And and to add and multiply the matrices, we first need to define two matrices that can be added or multiplied. Okay, you can just use the arithmetic operator in Python like plus, and it gives the addition of matrix. And the star operator, it gives a matrix multiplication. However, unlike NumPy, it does not give element-wise multiplication. Actually, in order to multiply things element-wise, you need to use the function like multiply element-wise. But SymPy is mostly a kind of, let's say, symbolic mathematics, and we are not using this feature much, element-wise multiplication much, because there are not many things to do with in the, let's say, mathematical work with this. So our default is the let's say textbook multiplication of matrix. Okay, and you can also try to use the add operator. Which is actually kind of explicit Python matrix multiplication operator. That can also be used for NumPy to mean the textbook multiplication than the element-wise multiplication. Okay, if you just want to multiply a matrix with some constant scalar value, you can just use the star operator, and it gives a matrix times 2. Okay. Where we need to put the init printing. Here. Okay. Okay. In order to okay, SymPy is quite strict about the matrix shapes. What do you mean by this is that, okay, if you perform the dot product of two vectors, which is 3 times 1 matrix, and it gives a result 1 times 1 matrix. And if you just add with some constant, then you get an error. Because this is actually a 1 times 1 matrix, then it is a number. And we are very strict of what you mean by strict about this is that in NumPy, you are able to add matrix with constant or multiply matrix with some vector that is implicitly, let's say, casted to the some NumPy matrix and allows multiplying numbers and matrix very easily. But for SymPy, it is very strict about the shapes. Okay, in order to add the, let's say, 1 times 1 matrix to some number, you need to index this completely to get the underlying constant, the underlying entry, and this doesn't give the shape error. Or if you like the another syntax, you can just use the dot rather than using the transpose multiplying. And dot operator, it does the transpose multiplying and gets the constant automatically. So if you favor this, you can use this also. Okay. And we also note about another helper for the IPython, where okay, which if I place the cursor to the right of the dot and tries to press tab, it right? Okay, it gives a number of the methods or properties that matrix class have. Actually, there are quite a lot of things, quite a lot of functions inside the matrix. Well, that is not, let's say, we cannot explain everything because there are too many. But if you want to browse through this, you can use this helper. Okay. And we are going to, okay. If you have any questions. Okay. We are going to move on to the linear algebra, and we need to show which matrix it came from. Okay, here is the matrix. Okay, we are going to introduce a couple of linear algebra methods like determinant or eigenvalues. Okay. In order to compute the eigenvalues of the matrix, you can use the eigenvalues interface. And it always gives a list of the, let's say, the dictionary where the keys are the eigenvalues and the values are the multiplicities. How many eigenvalues are repeated for this value. And this means that this matrix have the eigenvalue 2 times and eigenvalue 4 1 times. And unlike the, let's say, solver interface where the outputs can be very, very different, for the matrix, if you just want to, let's say, find the eigenvalues of the matrix, then the outputs are quite uniform, and it always be dictionary that that has only one way to interpret. Okay. And in order to get the eigenvector, you can use the eigenvector operator, and it is more complicated output, but what it really gives is that it gives the list of the tuples, and each tuple represent the first element of the tuple represent the eigenvalue, and the second one is the multiplicity of the eigenvalue. How many eigenvalues are associated with that specific value? And the third one is a list of the vectors that represent the eigenvectors. And you can get the full result. And you can maybe need to see how to iterate over. Okay, this gives an iteration of the values, and this gives iteration of the multiplicities, and this gives a value unknown. This prints out the eigenvectors only. Okay, it is a little bit complicated to, let's say, iterate, but that is still, let's say, structured. Okay, in order to solve a matrix equation, you need to use the matrix dot solve, and the right side hand side is the vector that represents the right side hand of the simultaneous linear equation. Okay, this is the result you get. And if you multiply with the original matrix, and you can see that this equals this matrix. Okay. And we are going to be introduced about some, let's say, how to use the matrix methods with the SymPy to, let's say, verify some complicated formula like Sheldon-Morrison. Okay. And here we are going to be, let's say, okay, I can just search this on the Wikipedia. Okay, Sheldon-Morrison formula is like this matrix identity where you need to think very, let's say, very involved in the linear algebra to verify this. But if you just want to calculate every entries individually and get some insights about how this works, then you can just create a SymPy matrix and try to compute the determinant and inverses and try to verify with simplify. And the other thing that can do with the SymPy matrix is to find things like the coefficient for the linear interpolation, where you can just solve the matrix entities, matrix with symbolic entities, and you get the same result as the theoretical one. But if you use the if you try to use the SymPy here, rather than solving all these things by hand or using some linear algebra, then you can more likely doing less mistakes. Okay. Any questions? Okay. And here we are going to check a couple of the difference of the symbolic and numeric matrices. Like like before we have about the solver, like a solver, SymPy mostly operates on the symbolic matrices. And let's say if you want to compute the eigenvalue of some, let's say 3 times 3 matrix, you can also get a very complicated result. That is because of solving cubic polynomial. And because of SymPy trying to solve the cubic polynomial very exactly, that is why you are getting the complicated result. However, if you feel like this result is not what you want and you would just want to get the result in decimal, then you would better use the things like NumPy. And yes, SymPy is not for this. However, there are some cases that you actually need some symbolic result. For example, if you want to count the number of the eigenvalues, then if you just compute it numerically, it is not, the two numbers may not be exactly the same. So if you want some things like if you, let's say, count how many eigenvalues there are, then you eventually need to use the symbolic matrix, and trying to use the numeric ones always are prone to error. Okay. Here we get a different result like, okay, here we get the eigenvalue 2 has multiplicity of 2, but here it is all treated something distinct because there are some numeric errors involved in these numbers. Okay, any questions? Okay. The other thing to note is about working with very large matrices in SymPy. We also need to be noting that SymPy matrix algorithms are designed to work for smaller sized matrices. And even though you would assume that the LAPEC things work with like 1,000 times 1,000 matrix, in SymPy, even for the 5 times 5 matrix, the result can get extremely slow if all of the entries are fully symbolic or something. And this gives very much huge slowdown. Okay. And similar, let's finding some inverse of the 3 times 3 matrix. And yes, so this means that anyway, this is, let's say, this have let's say 5 factorial number of terms. And generally, you do not expect like SymPy matrix multiplication or determinant to have, let's say, n cube time complexity, but you would generally assume that it should have really n factorial complexity. So you should not really work with too large matrix or the matrices that, even though it can be large, but the matrices that don't have, let's say, very, let's say, analytic solutions like the ones noted like the bilinear interpolation before. Okay. However, in order to work with very large matrix with SymPy, you should not, let's say, list every entries of the matrix as symbols, but would rather use the matrix expressions. The matrix expressions are, let's say, more lazy form than the matrix, where the dimensions of the matrix are now symbolic. In order to create the matrix expressions, you would first define the symbols with assumption that the integer, because the entries of the matrix, the index of the matrix should be integer anyway. And to similarly, the symbol constructor, you need to use the matrix symbol constructor. But it has 2 more arguments. First one is the shape of the row, and the second one is the shape of the column. And here we define the matrix expressions. And you can easily add or multiply the matrix expressions or finding the transpose of the matrix expressions. Yes, it also tries to expand the transpose with the matrix algebra. And you can similarly get things like shape. It is, let's say, n times n shape. Okay. Similarly, as how matrix operates, matrix expressions also assumes that shape should match or you get an error. Okay. Okay, if you can also create a symbolic matrix with the numeric shapes, and it doesn't list out all the matrix entries, but the values of the difference is that the shape of the matrix is now concrete numbers than some unknown number. Okay. And there are also like special functions to represent the matrix, special matrices. For example, if you want to represent a symbolic identity matrix, then you are not using I anymore, but use the identity with the shape, and it gives a. Okay, we are not using this one. It gives a identity matrix added with some other symbolic matrix. And similar with the identity, you can transpose or use this to represent symbolic determinant or trace or inverse. Okay, and additionally, like because of the because matrix symbols have shapes, there are some algebra that works conditionally when something is square or not. Okay, for example, the inverse here does not distribute because a times, although a times b is a square, a and b individually are not square. But here you can, if I define explicitly as a square matrix, then you can get that the inverse distributed to each matrix, and similar to the determinant. Okay. And even for the explicit matrix, you can use symbolic matrix operator such that it does not compute this yet, but represent more lazily. And you can add and multiply with other symbolic matrix. Okay, these kind of things are useful if some matrix is actually some constant and some matrix should be some symbolic matrix, some variable matrix. And if you want to list out the explicit entries of this, you can just use S explicit. Although if you try to use this to like 1,000 times 1,000 matrix, you get very big result. But you can use this to, if you need a concrete result of us, and try to expand each entry, each index of the symbolic matrix to the one single matrix. Okay, similar as how things work, you can also do substitution. This replaces the matrix C with the M that is defined before, and it tries to substitute the whole matrix. And this allows to evaluate further. It evaluates the identity, expands the identity matrix to each of the elements. Okay, in here we are also trying to define matrix symbol 1 times 1 and tries to multiply with, multiplication works, but trying to adding with this doesn't work like NumPy. Okay, you can similarly just to cast the, multiply the symbol, scalar symbol with identity matrix with some size to, let's say, vectorize this over this. I'm not sure if identity is the correct one, but sometimes you may need to use things like one matrix though. But, or also you can, yes, try to, and also if you try to do explicitly list all the elements, then you get this result. Or similarly, you can just get the entry of the symbolic matrix, and this is now scalar, and this can be added to the scalar. Okay, here are the exercises. If you have any questions. Okay. Yes, it's already
So,
break.
yeah, so we're going to have one last break. So we'll start up again at 4:30. And then when we get back, we'll go over the most important functions. Oh, you didn't do any recording on yours? All right, well, we might be missing bits of the recording then. I don't know when that stopped. All right, well, let's get started again. The last section. So yeah, now I want to go over code generation. So what do I mean by code generation? So code generation refers to the process of taking a SymPy expression and converting it into code from some other language or library. So SymPy supports generating code for a pretty large number of languages and libraries. So here's Python, which means generating code for NumPy or SciPy, C, C++, Fortran, MATLAB, Octave, Julia, Mathematica, JavaScript, LLVM, Rust, Theano, TensorFlow, PyTorch, and more. And it's also very easy to extend this to other languages that aren't supported yet. So the basic idea for code generation and basically using SymPy is you sort of have this three-step process. So first you use SymPy to derive formulas symbolically and model your problem using symbolic mathematics. Then you use code generation capabilities to convert SymPy into some numerical function, and then you use that numerical function to actually solve your problem with your data. And so, yeah, this section is going over the second step. So the most basic form of code generation in SymPy are the so-called code printers. So these just translate a SymPy function into a target language. So let's just use this function, absolute value sine of x squared, as sort of an example, and we can go over some of the code generating functions. So C code will turn this expression into C. F code will turn it into Fortran. We've got Julia code, JS code for JavaScript, Mathematica code, Octave does Octave, which is the same as MATLAB. Rust code, R code, CXX code for C++. Yes? C. Yeah, so by default, this is generating code for floating point inputs. So fabs is the C function for floating point absolute value, because C, I guess, doesn't have polymorphic functions, so you have to have a different floating point absolute value. Yeah, and then I think C++ just sort of inherited that from C, even though I think C++ does have polymorphic functions. So yeah, the exercise here is just to play around with these, create some function, some SymPy expression, and generate code for some of these languages, and see if you, yeah. Yeah, exactly. So I didn't really go over like why you'd want to do this, but there's a few reasons. One is, yeah, you can symbolically simplify your equations before you actually get something that you're numerically evaluating. Another reason you might want to do this is if your domain problem involves formulas that are simply too large and unwieldy to write out by hand. SymPy is very good at sort of doing the kind of bookkeeping that you wouldn't want to do by hand, and it can easily handle expressions that are pages and pages long, and then generate code for those. And that's something you'd never want to, try to type out manually or try to fuzz together by hand. But SymPy can do it pretty easily. Yeah. So one place where this comes up, the PyDy library that I mentioned at the beginning, this Python dynamics library generates what's known as the equations of motion for dynamical systems. And these equations of motion very quickly get, if you want to represent the dynamical system exactly, the equations of motion very quickly get very large. They're basically these enormous ODEs that are pages and pages long. And pretty much the only way to do this exactly is to generate them symbolically. And SymPy, this uses this module in SymPy called the sympy.physics.mechanics, which has a lot of functions for generating equations of motion. Okay. Well, so now we get to sort of what I would consider to be probably the most important function is if you're actually going to use SymPy in the for actual real work, which is this function called lambdafy. And so lambdafy is basically a bridge between SymPy and NumPy. So if you ever wanted to do numerical evaluation, but you still want to use SymPy to derive your equations, then lambdafy is what you want to use. So the way lambdafy works is you take some SymPy expression. So let's take our function here. And then you call lambdafy. So the first argument is the variable, and the second argument is the expression. And what this is going to return is a function. So f is now a function that can be numerically evaluated. And you can evaluate it on a single float, or you can evaluate it on a NumPy array. And so now this function f is this absolute value of sine of x squared as a NumPy function now. Just to note that this is considerably faster than, say, using SymPy to sort of numerically evaluate each of these points one by one with subs. That takes 2 milliseconds. If we use NumPy to numerically evaluate this, this takes about 1 millisecond. So, microsecond. This is about 100th. Yeah, so I think TimeIt ran 1 million loops on this one because it found it's like, oh, this is fast, so I can just run a bunch of these. And it only ran 100 loops on this one. So that's why the TimeIt call took longer, but the actual function is actually 100 times faster. So if you want to evaluate function at a lot of different points, basically on an array of points, you should use NumPy to evaluate that with that array of points, and then use lambdafy to convert your SymPy expression into a NumPy function. And so the way to think of lambdafy is that it's kind of like a magic way of writing this right here. So it's as if we had taken our function, this absolute sine of x squared, and written out lambda x numpy.abs x numpy.sine of x squared. And so this is actually why the arguments are kind of backwards from most other SymPy functions. You put the expression first and then the variable. In lambda-phi, you do the variable first, and that's because it's kind of like mimicking this lambda syntax. And so what lambda-phi is doing is, if we use this double question mark, we can look at the source code of f here, and we can see here it looks like it's just returning absolute value of sine of x squared, which is the original expression. But the key thing here is that in this function, this abs is actually the numpy absolute value function, and this sine is actually the numpy sine. So it's almost as if, just imagine that there's a from numpy import star at the top of this function. And lambda-phi will also, sometimes translate things from SymPy to numpy. So for example, in SymPy, the arc cosine is spelled ACOS, but in numpy it's spelled ARCCOS. And you can see here it's translated that in the source code for lambda-phi. And so how do we actually use lambda-phi to sort of do things? If you recall back in the solvers section, we talked about solving this equation cosine of x equals x. And we said you can do that with SymPy with nsolve, but maybe a better solution to do that numerically would be to use SciPy's fsolve function. And so if we look at sort of the documentation for fsolve, we see that it actually works very similar to SymPy's nsolve. It takes a function which evaluates whatever you're trying to solve, and that whatever you're trying to solve should equal 0, similar to how SymPy does it. And then you have an initial point. And so with that in mind, we can just take our expression, cosine of x minus x, lambda-phi it to turn it into a numpy function, and then call fsolve with an initial guess of 1, and that'll give us the same solution that we found with nsolve earlier. And so an exercise now is to solve these two equations from the previous notebook, but using lambda-phi and fsolve. fsolve is coming from SciPy. So fsolve is a numerical function. It works. fsolve itself does not know anything about SymPy. If you try to pass a SymPy, so let me just show you. If you were to try to pass a fsolve, if I had like this cosine of x, or I guess it's probably cosine of x minus x. If I have this SymPy expression and I try to pass that to fsolve, it's not going to like this. It's going to say, what the heck is this? Because fsolve doesn't, SciPy and numpy do not know anything about SymPy. So if you want to use SymPy in numpy or SciPy, you need to convert them into a numpy or SciPy function using lambda-phi. So yeah, if you try to just do it directly like this, you're sort of trying to skip this step process. You're trying to like go backwards here, and that doesn't work. You have to start with SymPy and then convert from SymPy into numpy. Yeah, it's not a function. I mean, even if you tried to make it a function, though, I think, I mean, you could even, yeah, I mean, you could try to do like something cute, like I mean, maybe this would work, actually. I don't know. If it does, it would be extremely slow. No, it doesn't. No, it still doesn't work. Like if you try to jam SymPy directly into numpy or SciPy, it's just not going to work. You need to convert the SymPy expression into a function, a numpy function with lambda-phi. Okay. Maybe I can just show the solution for that exercise. Yeah. Yes, yes. So actually, that is exactly what it's called. So, well, I mean, so yeah, PyCode. Well, so I guess by default, PyCode is going to generate for the math library. I think if you want to, use NumPy, you might have to use the printer directly. I don't know if there's a NumPy code. I don't think so. Yeah. So what you would have to do is probably from here. Maybe it's from, yeah. But I mean, it's, yeah. So that I think there's not like a convenience function for this because you wouldn't, yeah, usually. But yeah, you can. So these printers, we don't really go over it much here, but these printers are very customizable. You can subclass them to add printers for your own types of functions that they don't already know about. So if you wanted to use this, it would be like if you had a function that it doesn't know about, but if you want to say use it in Lambdafy, you could subclass this printer and then pass it to Lambdafy. So yeah, here's the solutions. fsolve, if you read the documentation, it supports a list of points, starting points. So that's how you can use it to find, multiple solutions. Obviously, unlike SymPy, you're not going to be able to find an infinite solution set. So maybe that's one advantage of a symbolic system over a numeric system, obviously. And then, yeah, so we also had this system of equations that we said we couldn't solve in closed form. And so if you look at how fsolve works, coming back here, this fsolve only takes one argument. So there's an example here in the documentation. So to solve a system with fsolve, basically the first element of the first argument is the first variable. The second element is the second variable. So if we want to do this with Lambdafy, we need to have a single variable that we pass to Lambdafy that encapsulates both x and y here. And so the way that we do that is there's this thing in SymPy called indexed base. And what this does is it lets you create a symbol that lets you index into it to represent sort of a symbolic array being indexed. And you can also do symbolic indices here. And so the nice thing about this indexed base is when you mix it with the code generators or with Lambdafy, you can now Lambdafy something like a of 0. And so this is now going to create a function that will access the first element of what you pass to it. So this a of 0 function evaluated on the array 10, 20, 30 returns 10. And so to solve our system of equations, we just need to create one of these index variables and then replace x with a0 and y with a1. So that we have something that we can actually pass to fsolve. And so now if we Lambdafy this, we can sort of verify that sort of works the way we expect it to. I guess we could also sort of really verify it by actually substituting in the original equations. So yeah, you can see this is evaluating the same equation. And so now we should be able to pass this Lambdafy function to fsolve. And if we go back to here, this should be the same solution that we found with nsolve, 0.45 and 1.11. Yeah. And so now, as an exercise, so I've shown it already a little bit, but SymPy has a plot function, which you pass an expression, and you can also pass a variable, like a tuple with a variable and a range. I think if you don't pass a variable, it'll just default to -10 to 10. And this sort of wraps matplotlib. But under the hood, this is using lambdaphi to convert this into a function that evaluates on a NumPy array, because that's how matplot works, is it uses NumPy arrays. And so as an exercise, write your own sort of little toy plot function that lambdafies the expression and then plots it with matplotlib, this plt.plot function. And this paragraph sort of goes into details on how that works if you're not familiar. And yeah, this in general, if the SymPy plot interface is sort of like too constrained for what you're looking for and you want to plot SymPy functions, this is sort of the recommended way to do sort of more advanced plotting with SymPy, is to just use lambdaphi and sort of manually do whatever it is you're doing with the NumPy array, whatever it is you want to do. So I don't know. Well, I guess we're probably fine on time because the last notebook's not very long.
So if I use, so maybe it's symbolic and all this other stuff, it's going to be faster and better than matplotlib on its own, or is this just a way of calling matplotlib?
Are you talking about the plotting specifically here?
Well, yeah, figuring out the points and then running.
Yeah, well, so the SymPy plot function, like it's a nice wrapper, but like, you know, matplotlib lets you customize a plot like however you want, like arbitrarily. But SymPy, it's sort of like, you know, it puts like this little f of x here and this x here, and it sort of, you know, does like a range for you, and it makes the line blue. And if you want to change any of those details, like you can do it with matplotlib. But for this example, no, it's not about the difference with performance. It's about if you wanted to do this manually, it would be so that you could have more control over what's going on. But it's also just to show that it's not that difficult. I mean, I guess spoilers, but like, yeah, that the solution to this exercise should only be 2 lines. Yeah, you can change how many points are plotted. You can. Oh yeah, I mean, yeah, I guess you can. Yeah, like this is what SymPy does when you plot the tangent function. But I mean, if you don't like this, you could sort of. I mean, SymPy probably should be smarter about singularities when it plots things, but right now it isn't. But you could like manually, you know, filter out the singularities and plot things yourself. Well, matplotlib, you would need to manually make the function, take the function tangent, take an array of points, and calculate it on that array, which is what plot is doing here, and what the solution of this exercise would do. So, you know, if one of those points in your array is near a singularity, you're going to get a plot that's similar to this. But if you want to be more careful about, you know, how you plot the singularities, you can do that you would have to do that sort of manually. I think SymPy, yeah, it needs to have better support for plotting functions with singularities. Yeah, Yeah, you need it's actually something that I think you can use symbolics to sort of symbolically solve for the singularities. So yeah, here's the solution. Well, okay, I guess it's 4 lines of code. So yeah, you convert the function to, convert the expression to a function, create an array of x values. Here I used 1,000 points, just, you can use whatever number you like. Evaluate that array on your function to get the y values, and then call the matplotlib plot function on the those x values and y values. Yeah, so SymPy is doing this, and it's also like adding some like labels and doing some stuff by default. There are some options to that, yeah. So if you look at the help for plot, there's like some options here. So I don't know why it scrolled down. So you can see like there's this label option, but like the options here, I mean, there's a lot of them, but this is nothing compared to what you get directly from matplotlib. Like even just the options to the plot function, you can see there's a ton of stuff. And then of course, if you know how to use matplotlib, you can directly manipulate the plot once it's created. So yeah, hopefully this gives you an idea of some of the power of code generation and the lambda5 function. Okay. I guess we've got a half an hour left. So so the last section is just a little bit of how to sort of how SymPy expressions work under the hood, so that you can understand how to do any kind of expression manipulation that you would want to do, even if it's not directly supported by a SymPy function. So if you take a function, a SymPy expression like x squared plus x times y, SymPy is going to represent this as an expression tree. And so graphically, that would be something like this. So the topmost expression is an addition. This left expression here is a power consisting of x and 2, and then this right expression is a multiplication consisting of symbol x and symbol y. And so the way we can see this is this srepr function in SymPy will print out an expression in this long form. And so we can see that the long way to create this expression x squared plus x times y is add of pow symbol x integer 2 comma mole symbol x symbol y. So if we break this apart, we can see it's the same as this graph here. We have this pow here. Pow is short for power. So we have a power of x and 2, so that's going to be x to the power of 2. And then a mole, which is a multiplication consisting of the symbol x and the symbol y. And then both of those two are the arguments to add, which is the class for addition. And so if we look at the two important attributes on any expression are the func and the args. So the func is usually just the type of the expression. There's some cases where it's not, but you can think of it as just the type of the expression. So the func of this expression is add, because that's the top level expression is an addition. And then the args are the arguments that you would pass to add. So in this case, the args are x squared and x times y. And if we drill down into, say, one of these arguments, say the first one, we can see that this first one, its func is a pow, and its args are x comma 2. And so by drilling down into the args of an expression and these sub-expressions, we can sort of access any part of the expression tree. And so the key thing with func and args is that you can use them to rebuild an expression. So if I take this expression and use the func on it, and then use star x per args. So the star is here so that it's called like, so the star here makes it so that like the args would be x squared and x times y. The star here just makes it so that these are the direct arguments of the function. If I didn't have the star here, it would be something more like this with a tuple. And so the star makes it so that you don't have to, it sort of denests that tuple in Python. And you can see that this is the same as this, which is, this is the same as this, which recreates the expression. And we can use I don't know if I go over this. Yeah, we can use remember that equals, the double equals operator always checks direct exact equality. So we can check, for example, here, if I do this double equals this, it should always give true. So this identity here should be true for any SymPy expression. The other thing to note here is that all of the numbers are wrapped with integer. So just like we discussed at the very beginning of the tutorial. So typically you don't need to care about this. You know, if you can just write x plus 2, and even though 2 is a Python integer, it'll automatically coerce it inside of, it'll automatically coerce it to a SymPy integer. But the reason that this matters is that this means that everything inside of args is going to have this same uniform interface. So even though this is a 2, it's still, 2 itself has an args, and it's just going to be an empty tuple because it's a leaf node of the expression tree. And so because of this uniform interface, it makes it easy to recursively drill down into an expression. Another thing to be aware of is if we look at x minus y, we can see that this here is maybe not what we would have expected. So x minus y is actually represented, we can see here, as x, so the add of x and -1 times y. And the same thing with if you do x divided by y, or 1 divided by x also, this is represented as x times y to the -1, and 1 over x is just x to the -1. So SymPy doesn't actually have classes for subtraction and division. It only has classes for addition and multiplication and exponentiation. So x minus y is actually x plus -1 times y, and x divided by y is x times y to the -1. And this might seem kind of annoying, but it's actually useful because it means that you can deal with these expressions in a much more uniform way. You don't have to necessarily care if something's an addition or subtraction. It's always just going to be an add, and then the coefficient, whether the coefficient's positive or negative, will determine whether it's a subtraction or something. And then, yeah, the actual way that like things are printed is sort of separate from how things are represented internally in SymPy. So here's an exercise. Use the nested args, so something like this. So drill down into the args of this expression here to access the 3. And you might have to do this sort of iteratively. Yeah, so I mean, you like all of these like algorithms. They don't like to them subtraction is just addition with a negative coefficient. So you would just have to write the same thing twice, basically. Yeah. So you might have noticed if you do this so you can see like we need to get the 3's over here on second argument, and then we need to continually do .args. You might have noticed, for example, here, actually I think even there it's like the arguments are not always necessarily in the same order that they're printed. So you kind of just have to look at it if you want to do it. Like here, for example, this expression is 2 to the x plus 3 plus z. But if I look at the args, actually SymPy has put z before. It's because when for addition and multiplication, SymPy will actually sort the arguments since they're commutative. So yeah, you'd have to, you kind of have to, you can see here, you have to drill down sort of piece by piece to actually find it. And this ends up being the answer. I guess there was another exercise here to create these expressions directly from the classes. So so yeah, here's I guess the most so there first off, I guess is worth noting that this add and this mul, you can pass as many args as you want to. And then yeah, for x minus y over z, you have to use -1 times this to get a minus sign, and then z to the -1 to get this division here. And so yeah, that basically with these building blocks, you can sort of build any sort of algorithm up that you want. You just need to remember these important facts, which is that SymPy expressions are immutable. So whenever you want to do something, you have to create a new expression. And secondly, that SymPy expressions should always be compared exactly equal with these equals operators. And so, for example, here's what a simple replace algorithm might look like something similar to subs. So basically, most algorithms that you would write with this are going to end up being recursive algorithms. So you can see here, replace is called recursively. And so, yeah, the base case of the recursion here is going to be actually, well, I guess both of these blocks are going to be the base case. So this is going to take this expression and replace x with y inside of it. And so as a base case, if the expression is equal to x, we just return y. Also, if the expression doesn't have any arguments, that means it's a leaf node of the expression tree. then we just return it as is. So that'll be something like a symbol or a number. Otherwise, we create a set of new arguments, and for each argument in the expression, we recursively replace the argument and then recreate that expression with the new arguments. And so, for example, here, if I take this expression that we had before and replace x with 2x, this is going to recursively go through that expression tree that we looked at here. And when it sees an x, it'll recreate this expression with 2x. And when it doesn't see x, it'll just recreate it with the same arguments. And so it'll end up being the same thing. And yeah, there's an exercise here, but maybe a little more advanced exercise. So I guess optional. If you want to do it, you can try it. Otherwise, I think maybe can open the floor to any questions, just general questions about SymPy. If there's any features you want to know about that we didn't cover today, we're happy to show those. Or yeah. I can try. Not actually. So one of the things about SymPy is that it's got so many features that I don't think any single core developer knows about all of them. And I, in particular, am fairly weak on most of the stuff in the physics submodule, including units, but I will give it a shot. Do you know anything about the unit systems module? I mean, I would probably just have to look up the documentation. Oh no, that's not what I wanted. Okay. I know how to get to the docs for it. Yeah, so I think the unit systems module it's kind of different than most unit modules in other Python libraries, because it's based around this idea of like these systems of units. So you can have different systems of units, and the mathematics behind it has to do with like this idea of like this group structure on units. So you can have a unit system where your base units are like, I don't know, whatever the CGS base units are, like centimeters and grams or whatever. Or you can have like the SI system where you've got kilometers or kilograms and meters. And yet there's some this is the part where I'm not completely familiar with how it works, but I guess you set up a base system, or there's some predefined ones like CGS, and then you can convert units into the base system. And of course, it also represents constants symbolically, which is another advantage over most numerical unit systems in Python. There's also YT has a library that it uses called, I don't know how to pronounce it, unit. It's on UNYT. And that's a NumPy library that adds units to NumPy, but it's actually using SymPy internally to represent the units. And it's not using this module, it's just using basic SymPy symbols, but internally it's using SymPy. And of course, there's other unit modules for NumPy arrays that don't use SymPy. Like I think, I forgot what the most popular one is called. Maybe, I don't know if anyone remembers. You have anything that you can add to that? Okay, sure. Go ahead and plug it in. Yeah, if anyone has any questions like that about like some module or some part of SymPy we didn't cover, I'd be happy to at least give it a shot. If depending on how well we actually happen to know that. So what he's showing also right now is SymPy Live. It's live.sympy.org. And what this does is it actually runs in your browser using Pyodide. So it's a SymPy shell that runs locally on your browser. It's Pyodide. It uses WebAssembly to run SymPy inside your browser. So, yeah, it's WebAssembly basically. No, speed of light is a constant that's defined, and it's actually, you can see, symbolic constant. But it's defined, well, you can convert it to kilometers per second, and that's giving some exact value for the speed of light in kilometers per second. It's not a number, it's a unit. C is a number with a unit attached to it. C is not a number. It's a number with a unit attached to it. Depending on what units you're in, it'll have a different value. No, so that's the point, is there's different unit systems that are defined. It's not just, it doesn't just default to like SI. You can use any unit system. So you can do kilometers per second, you could do miles per hour, you could do yeah, or you can just represent it symbolically like as C, and then when you have whatever formula you want, you can convert that to whatever unit. Well, so C, I think this actually is probably going to be an exact value for C, this rational number, because it's defined, the meter and the second are both defined in such a way that C has an exact value. That's just, I mean, I don't know if anyone can confirm that, but I believe that's true. I think it's the kilogram that recently changed its definition. I don't know if SymPy's been updated for the latest definitions. Wait, why did it stop working? Oh, I think there's probably a function convert to, not a method that you want to use. It's just a function. I don't know where that function comes from. Yeah, it comes from the units module. If there's no other questions, I think we're done. So